This video is about the procedure of diagonalization. Diagonalization is basically converting a matrix, a square matrix A, into a diagonal matrix. That is, if we have A being n by n, it is converted into a diagonal matrix, also square and n by n. And remember, a diagonal matrix has zeros on all the elements except for on the diagonals. So just to remind you about the structure of a diagonal matrix. And you can imagine that if you have a system of equations that is described with a diagonal matrix, then it's already in row echelon form. And thus diagonalizing A would be an effective way of solving this system of equations. And so that's what we'll talk about doing here. Your objectives here in taking notes of this video, and that will be assessed in the problem sets, will be you will develop the ability to recognize whether a matrix can be diagonalized in the first place, and if so you'll use that method to solve a system of coupled ordinary differential equations. So diagonalization is essentially a linear transformation or you can also think of it as a coordinate transformation of matrix A. In other words, the transformation is to project matrix A along a coordinate system such that the transformed matrix only has non-zero elements on the diagonal. So let's do this transformation on the following coupled ordinary differential equations. So here we have in matrix form, we have vector x prime is equal to the coefficient matrix A times x, where x is equal to x of t and y of t, and x prime is equal to the derivative of x with respect to t and the derivative of y with respect to t, where of course t is the independent variables and our dependent variables are the elements of vector x, being x and y. So let's define a transformed vector, and we'll denote that vector as x, the vector x with a tilde over it, and we'll define it by as it's related to vector x by a linear transformation. It does it transforms the transform vector to the reference vector. And so likewise, x prime, the time derivative on the left-hand side of the equation, is equal to q times x tilde prime. And that's the same thing as q times x tilde prime, because q is independent of t. There are none of the elements of q depend on t in this example. So the derivative of x is just equal to q times x tilde prime. So with that, with those definitions, our original equation, x prime is equal to ax, becomes q x prime x tilde prime is equal to a, and again we've defined and again x is equal to q times x tilde. So now if q is invertible, or we've defined q such that it is invertible, then we can pre-multiply both sides of the equation by its inverse. And of course, q by the inverse of q times itself gives the identity matrix. And we have a new system where x tilde prime is equal to q inverse a q times x tilde. And if q is such that its inverse times a times q is equal to a diagonal matrix, then we have the following. X tilde prime is equal to d x tilde. And since it's diagonal, this is a list of uncoupled ODEs. That is, the time derivatives of each element of x tilde only depends on the corresponding element of x tilde. We have an equation in reduced row echelon form, which is an uncoupled system of equations. And we just need to solve each of those equations directly as a ODE, with this case a constant coefficient. Okay, so that's an example of how we would apply this method of diagonalization to solving a system of originally coupled ordinary differential equations. Let's talk about how to do this diagonalization. And we'll start with 4 theorems. And theorem 11.4.1 really summarizes the method of doing the diagonalization. And it states that if A is square, has dimension n by n, then A is diagonalizable if and only if it has n linearly independent eigenvectors. So that's the first requirement of A being diagonalizable. And so you need to check whether A has n linearly independent eigenvectors to use this method. The second part is to make the eigenvectors to be the columns of the matrix Q. And then the operation Q inverse A times Q gives the diagonal matrix sought. And D has the jth diagonal equal to the jth eigenvalue. So on the diagonals of D are all the eigenvalues of the matrix A. So that's the first theorem. The second theorem is 11.4.2. And that says that A has eigenvalues, if A has distinct eigenvalues, lambda 1, lambda 2, all the way out to lambda n, then the eigenvectors are linearly independent. The eigenvectors are orthogonal to each other if all the eigenvalues are distinct. The next theorem, 11.4.3, states that if A has distinct eigenvalues, it is diagonalizable. And that's, I guess we know that A is diagonalizable if and only if it has n linearly independent eigenvectors. The next theorem states that if the eigenvalues are distinct, then the eigenvectors are linearly independent. And then following from that is therefore A is diagonalizable if the eigenvalues are distinct. And the last theorem, 11.4.4, states that every symmetric matrix is diagonalizable. And that also follows from Theorem 11.3.4, which states that every symmetric matrix has n orthogonal linearly and thus linearly independent eigenvectors. Just to remind you of where this property of symmetric matrices. So those are the key theorems you need to know about diagonalization. I'd like to give you a sense for why Theorem 1 works. I'd like to go through a proof of this first part. Well, actually, the very first part of part 1. So A is diagonalizable if it has n linearly independent eigenvectors. So proof that A is diagonalizable if it has n linearly independent eigenvectors. So given that it has n linearly independent eigenvectors, let's put the n Li eigenvectors into the columns of Q. That is, Q is equal to, has as the first column, the first eigenvector, the second column, the second eigenvector, and so on, all the way out to the nth eigenvector. So there are n columns, and each vector, of course, has n elements in it. So if let's multiply A times Q, and when we do so, we see that A is multiplied by each of the columns of Q, which are the eigenvectors, and that forms a new matrix with the columns being the individual vectors being the product of A with each eigenvector. And since the E's are eigenvectors, we know each of those products is equal to the eigenvalue times each eigenvector. Right? So the product of A times Q in the first column is A times the first eigenvector, and that is equal to lambda 1 times the first eigenvector. And that's true. Likewise, A times the second eigenvector is the second column of this product matrix, and that column is equal to lambda 2 times E2, and so forth. And so we can write that right-hand side as a matrix our matrix Q containing our eigenvectors times a diagonal matrix containing the eigenvalues. And from there, we know that since the eigenvectors E1, E2, all the way out to En are linearly independent, then the determinant of Q is not equal to 0, and thus Q has an inverse. It's invertible. So multiplying both sides of the above equation by the inverse of Q gives Q inverse times A times Q is equal to Q inverse times Q times D, where this is, again, this is Q right here, and this is D, the diagonal elements containing the eigenvectors. And this, of course, Q inverse times Q is just equal to I, so the right-hand side is equal to D. So this shows A is diagonalizable if it has n Li eigenvectors. And so we've successfully proved the first part of the first theorem of diagonalization. And I encourage you to see page, page 571 for the proof of the second part. That if and only if the eigenvectors are linearly independent, then A is diagonalizable. Noticing I spelled diagonalizable, I got kind of tongue twisted and spelled diagonalizable wrong. Let's see if I can do it right this time. Diagonalizable. Good. Okay, now let's look at an example. Let's return to our example of solving a system of coupled ODEs. So in Greenberg's example, X1 is equal to the concentration of a chemical species in a reaction, in a chemical reaction, and T is time, and X2 of T is the concentration of another chemical species in the reaction. K12 and K21 are the coefficients determining the rate of transfer between the two species. That is, from x1, part of it is transferred or becomes x2, and the rate is proportional to k21, and x2, part of x2 is converted to x1 by the chemical reaction at a rate that's proportional to the coefficient k12. Therefore, the rate of creation of x1 as a function of t, so again, this is the rate of increase of x1 with respect to t, is equal to the loss due to the reaction that creates x1 So the rate that x1 is converted to x2 is proportional to x1, and again it depends on the coefficient k21. So that's a loss of x1, but there's a gain of x1 by a transfer from x2. And a similar equation can be written for the rate change in x2 as a function of t, the rate increase in x2. That being k21 times x1 minus k12 times x2. This is the gain of x2 from x1 and the loss of x2 due to the transfer to x1. And this describes a system of coupled ordinary differential equations where the vector x prime is equal to a times x, where a is the coefficient matrix describing these with the coefficients for these rates of transfer. And because of these transfer rates, the system of ODEs is coupled. And so in order to solve for x1 and x2 as a function of t, the strategy will be to diagonalize A. So we first have to find the transformation matrix Q. And of course, and so the columns are the eigenvectors of A. And the eigenvectors, well, first of all, the eigenvalues and vectors for A are, so the first one is lambda 1 is equal to 0, and the first eigenvector is equal to alpha times k12 times k21. We know this because we can solve the eigenvalue problem for A, and lambda 2 is equal to minus k12 plus k21, and the eigenvector for that, E2, is equal to beta times 1 and minus 1. So we have the eigenvalues and the eigenvectors. And therefore the Q matrix is equal to E1. The first column is E1, the second column is E2, and that gives K12, K21, In general, these are multiplied by alpha, where alpha can be any number, right? So again, there's an infinite number of eigenvectors here, but we just need one because everyone will have the appropriate property that we want to solve the equation. We don't need all the eigenvectors to solve the equation. We just need one pair of eigenvectors to do so. So we'll define our Q matrix based on these eigenvectors. And remember, x tilde prime, again from the beginning of the lecture, is Q inverse A Q times x tilde, and that is equal to our diagonal matrix x, diagonal matrix D times x tilde, it's a vector, and that's equal to lambda 1, lambda 2 times x tilde. And thus we have the uncoupled system of equations. X tilde prime 1 is equal to lambda 1 x 1 tilde, and x tilde prime 2 is equal to lambda 2 x 2 tilde. And the general solutions, this is a first order ODE with a constant coefficient and it's homogeneous. Our x1 tilde is equal to c1 e to the lambda 1 t, and x2 tilde is equal to c2 e to the lambda 2t. And of course, lambda 1, if you might recall, is equal to 0, so that just gives c1 for the first solution. And lambda 2 is minus k12 plus k21 t. So these are solutions for the transformed vector components. We need to find the original concentrations. So the original, or the concentrations, are x1 and x2 as a function of t, not the transformed compositions. And to do that, we just do the transformation operation back to our original vector by q multiplying q times x tilde, and that gives x1 x2 is equal to k12 1 k21 minus 1 times c1 times c2 e to the minus k12 plus k21 t, and that gives the final solutions that x1 is equal to k12 c1 plus c2 e to the minus k12 plus k21 t, and x2 is equal to k21 c1 minus c2 e to the minus k12 plus k21 t. And that's our final solution for this example of a coupled chemical reaction between two chemical species. Okay, so again, you should be able to recognize now whether a matrix can be diagonalizable, or whether it can be diagonalized. And if so, you know how to diagonalize a matrix and solve a system of coupled ordinary differential equations.